Hey everybody, this is a chem842 lecture for my um, medicinal chemistry course on physicochemical parameters and chemical informatics tools. I'm recording this in April as well, past the heart of COVID when I did most of my online recordings. But I updated this lecture because some of the tools have changed and some of the workflows have changed for like using these tools. So physicochemical parameters are going to be parameters related to drugs, small molecule drugs, that have to do with like drug likeness and oral bioavailability and things like that. Some simple things like molecular weight, number of rotatable bonds, hydrogen bond donors, hydrogen bond acceptors, all these kind of things. And so we're going to discuss those and how they relate to oral bioavailability. We're also going to talk about chemical informatics tools. So these are pretty nice web-based tools that we can use to take a chemical structure and determine these properties, and maybe make predictions about drug absorption and oral bioavailability. One thing I do want to do before we start is just to remind you, you should be pretty comfortable with the concepts of phase 1 and phase 2 metabolism. Not you may have to review them a bit, but like hopefully you got that out of the last lecture, and I'm just going to show the PDF real quickly of one of the PDFs from the last lecture, which is kind of talking about phase 1 and phase 2 metabolism. This just sort of summarizes the whole idea. What does phase 1 metabolism do? It usually modifies the chemical structure, changes the functional group arrangement, or in this case it turned a tertiary amine into a secondary amine. We talked about how that happened. It would probably hydroxylate the methyl, oxidation, and the alcohol would swing down, kick off formaldehyde to reveal the secondary amine. And then phase 2 metabolism would be typically like attachment of a conjugating group, like in this case glucuronic acid, which kind of looks like glucose, etc. And there's different phase 2 metabolism reactions, different phase 1 metabolism reactions. That was all the last lecture, and in order to understand this lecture, you should be a little bit familiar with those things. You may want to review them and stuff. Let's see, what else on the outset. Normally the lectures are supposed to be about 2.5 hours long. Since there's going to be a lot of cases where you're going to be sort of expected to use a computer to use these tools, I'm assuming that that's going to take time also. So I'm not going to aim to do 2.5 hour lectures for this week and next week, but maybe 2 75-minute lectures or something like that. I also think the extremely long lectures just don't work too well. So yeah, let's see, what else? Anything else on the outset? I'll jump into the next slide, and complementary reading material for this stuff. There is a pretty good book that is called Drug-like Properties, Concept, Structure, Design, and Methods from ADME to Toxicity Optimization, that really talks about all these concepts and has a lot of real examples. Edward Kearns. If you're interested in this stuff, this might be a good book to buy. It's not critical for our course. I think it might cost a little bit of money too, maybe 100-ish or more dollars, but it's definitely a good book if you're interested in a career in drug discovery. What's the overall agenda? So first we're going to talk about physicochemical properties. In general, we're going to review the concept of oral drug absorption through the GI tract and how drugs physically move through the GI tract and wind up in your blood, usually, to reach a drug target. We'll talk about aqueous solubility, so log P and C log P are two measures of aqueous solubility. We'll also talk about something called polar surface area, PSA, and TPSA, topological polar surface area. And these are other parameters related to drugs that, as you might imagine, is a measure of how much of the surface area is polar, basically. Then we're going to talk about two rules or strategies for determining drug likeness. One's called the Lipinski rule of 5, and there's others, or a set of rules are called the Weber rules, and they're just specific rules, and we'll go through them all. From there, we're going to move on to sort of chemical informatics, which is using computers to basically determine parameters and all sorts of cool things you can do with computers related to drug-like substances. A lot of these are web-based tools. We're going to talk about something called SMILES. SMILES is a chemical representation of organic molecules. So we'll learn about the basic idea of that, and we'll then use SMILES to do different things like generate 2D and 3D structures. We're going to use these SMILES strings to predict drug likeness using the Lipinski and the Weber rules. We're going to predict metabolism. That's going to be fun. So that's where we come back to that idea of phase 1 and phase 2 metabolism. And using computer tools to predict metabolism. It's a pretty cool idea. We're briefly going to go into a couple other things. Virtual screening. Using the concept of like screening molecules against a drug target using computers. And it's not a perfect thing, but we're going to give some background on that. In silico synthesis, that sounds kind of fun. It's basically the idea of doing synthesizing molecules in computer for the purpose maybe for virtual screening or something like that. Homology modeling is just another thing we're going to mention. That's basically creating structures of proteins, creating structures of proteins that if you don't have a crystal structure, like an X-ray structure or a cryo-EM structure, it's a pretty cool biochemistry tool for that. Docking, we'll mention docking. Docking is kind of the idea of if you got a chemical structure of a drug, ligand type thing, and then you have a protein, the idea of having the drug bind to the protein into a binding site or active site. Molecular dynamics, we're just going to briefly mention also. The idea is that you can let the protein, either protein by itself or protein maybe with a bound drug in a receptor, equilibrate. So it let all the amino acids move around and equilibrate, kind of like we do in the real world, right? Like how proteins are not static, they're very dynamic. I'm going to have a couple case studies related to my research that use some of these tools, and that'll be kind of a fun thing also. Alright, so moving forward, first thing we'll talk about is basic oral absorption through the GI tract for small molecules. So drug absorption for drugs that you absorb or administer orally occurs in the stomach or the small intestine, so it kind of depends on the pKa and ionization state of the drug. Interestingly, as you go from the stomach into the small intestine, the pH increases, so it goes from acidic to less acidic, and this sort of shows that whole process. Drug would be consumed orally and first enter the stomach, and then as it proceeds, it'll proceed through the duodenum and the jejunum and the ileum. These are all part of the small intestine, and then that continues into the large intestine. And usually, most drugs will be absorbed in the stomach or the small intestine. And so the pH increases as I mentioned, from the stomach to the duodenum to the jejunum and to the ileum. And so this kind of shows the pH, often a range, as as you proceed through the series of organs. And um, it also depends a little bit on whether you're fasted or fed. If you're fasted, it's usually a little bit of a lower pH. If somebody's fed, the pHs are often a little bit higher. And also the transit time, so how fast the drug is absorbed, varies between the stomach and the small intestine. A drug's protonation state can affect its ability to absorb at these different stages also. So we to really understand this, we have to consider any functional groups that are present, and their pKa's, and that allows you to determine the amount of protonated versus neutral forms of the drug. So as an example, naproxen is, let me move my face out of the way. Let's see if this works. There we go. Naproxen is a carboxylic acid, and it has a pKa of 4. And so depending on what the pH environment is, it's either going to be protonated or unprotonated. All right. Whereas fluoxetine or Prozac, the antidepressant drug, it is a basic compound, and the pKa is around 10. And it also will depend, it's either going to be protonated or deprotonated. To be neutral, obviously, in the top case, you want it to be protonated, and in the bottom case, if you want it neutral, you want it to be deprotonated. So, and as you can imagine, this is all going to depend on the pH, and we can use the Henderson-Hasselbalch equation to actually calculate the amount of ionized versus unionized versions of these molecules. So that's exactly what we're going to do next. To quantify the amount of neutral permeable drug molecule at a specific area in the GI tract, we can use the Henderson-Hasselbalch equation. So this is an equation you probably learned in Gen Chem or maybe biochemistry. It's a pretty simple formula. There's a couple versions of it. There's the version for weak acids, so that would be like naproxen with the carboxylic acid. It's pH equals pKa plus the base 10 logarithm of the ionized version divided by the protonated version. So we'll ideally want a lot of the protonated version, which is neutral. And the pKa, of course, is the pH at which 50% of the substance is ionized. Also, another thing to remember, pH is kind of an experimental quantity, and it kind of depends on the the environment, right? And it can change. pH can change. pKa is a constant. pKa refers to the functional group, and like in the case of naproxen or Aleve, the pKa is 4. It doesn't really change. Most pKa's don't change given a molecule. For a weak base, and that would be the case of fluoxetine or Prozac, pKa is, well, the formula is different. It's pH is equal to pKa plus the log. But in this case, it's the base on top, which is the neutral form, divided by BH plus, which would be the protonated form. I was able to restore my little yellow pointer thing, which I learned how to do during the COVID remote teaching. Anyway, let's look at a couple of these molecules, how they transition through the membranes. We'll also practice the Henderson-Hasselbalch equation, which is a pretty easy equation. And we'll also we'll talk about how do these molecules actually transition through a membrane, and so we'll show that next. Also, remembering that there's 2 versions of the formula. Okay, so passive diffusion is the way most drugs are absorbed, and they basically just go right through a GI tract membrane. It could be into a cellular target also, but basically, typical biological membrane. It requires the drugs to be sufficiently lipophilic and neutral. Okay, so this is an example of how a membrane would look. There's water on both sides of it. The middle part is sort of fatty acid type groups with a polar head group and a sort of greasy chain, and it's on both sides, and these could be fatty acids, it could be phospholipids, etc. So basically the drug, if it's sufficiently lipophilic, will basically transition through this sort of nonpolar environment. Not absolute. So polar and ionic drugs can still be absorbed through the paracellular space. So that's like a little gap between epithelial cells. So there's other ways that drugs can transition through. It's not the only way, but this is a very common way. Overall, drug absorption can occur through a couple different methods and ionization states in the stomach, duodenum and the jejunum and the ileum. But generally speaking, it's this kind of strategy, and it sort of requires drugs to be neutral. Okay. So what we're going to do now is we're going to calculate the A minus over HA, which basically tells us how much of the neutral molecule there is. We're going to do this for naproxen. We'll also do it for fluoxetine, which is Prozac. We're going to consider two different sites of entry, the stomach and also the ileum, which is in the small intestine. And in the stomach, the pH is -2, and the ileum, in a fasted state, the pH is -8. And so we're also going to do the same thing but for fluoxetine under the same conditions. So this will be a fun kind of exercise of the Henderson-Hasselbalch equation. And remembering that there's kind of two versions, one for acids, one for bases. Great. I realized there's a little error in my PowerPoint. This says fasted state stomach pH -2, but should really be pH 2. I'll correct that in the PDF file that I upload. So make a note to do that. However, my calculations are fine, and so it's just this little top part is incorrect. So in the PDF that you're going to see, you will, it should hopefully say pH equals 2. Okay. Alright, so the equation is pH equals pKa plus log 10 of A minus divided by HA. And all we have to do is really plug in the different values for the pH and the pKa. Remembering again that pH is sort of variable and changes in the environment. pKa is a constant. Okay, so what's the pH? What's the pKa? So the pH is 2, not -2, which says up there. And the pKa of the functional group is 4. So all we have to do then is move the 4 to the other side, and it becomes -2 equals log 10 over A minus divided by HA. And we're going to solve for A minus divided by HA. All we have to do is take 10 to the left equals 10 to the right of these, and then the logarithm goes away. So we just do this on both sides, and then 10 to the -2 is a small number. And when we just consider the top as A minus and the bottom is HA, you'd say, well, basically you have about 1% ionic and 99% neutral, which is roughly the case. And that's actually pretty good. And it shows that this drug is pretty efficiently absorbed in the stomach because it's mostly neutral. Rapid onset absorption, and you get about 30 to 60 minutes before it's absorbed, so it's pretty effective, especially for a little painkiller type drug like this. Okay, so now we're going to consider naproxen in the ileum, which is a higher pH that is more closer to neutral, I guess. And we basically do the same exact formula. pH equals pKa plus log 10 over A minus over HA. And we do the same kind of math. 8 equals 4 plus the logarithm. And all we have to do then is move the 4 to the other side. Now it becomes 4 on the left, and then 10 to the x, do the same kind of math, and then you can see that now in this more basic environment, A minus is much more deprotonated as expected, so it's about 10,000 to 1 ionic to neutral, and as you might expect, this is not a very efficient place for the drug to be absorbed. And so generally speaking, we think of these carboxylic acids like naproxen to be absorbed more in the stomach than the ileum. So very bad, unlikely to be absorbed in the ileum. That would be the reasonable conclusion. Fluoxetine is the opposite situation. It's an amine, so its protonation's opposite in the stomach and the ileum. And so if we, again, this is a typo up here, it's not -2, it should actually be 2. Remember the Henderson-Hasselbalch equation for base-containing compounds is slightly different. So how's it different? This is the equation. pH equals pKa log 10, that's base over BH plus. And so to do this, we just fill in the numbers, and pH is 2 in the stomach. Again, wrong up there, right here. pKa is about 10 for the protonated amine, right? Because an amine itself doesn't really have a pKa, a usable pKa, so you have to consider the protonated state of the drug. So, and when it's protonated, the pKa is 10. Okay, and it's B over BH plus. So to do this, we just, same thing, we move the 10 to the other side. Now it becomes -8. Solve 10 to the x on both sides. So it's 10 to the -8, and it's basically a very tiny number. It's, it's 7 zeros and it's 1. And on the top is the neutral form, and the bottom is the protonated form. So it's basically it's an extremely small amount of the neutral form, and you'd say 99.99% protonated, which is the inefficient form to absorb. And so we say it's very bad, it's almost entirely protonated, does not absorb well in the stomach, right? That would be the conclusion. Okay, and so then what about the ileum? Same drug, pH is different, it's all going to be handled by the Henderson-Hasselbalch equation, do the same thing. pH equals pKa log 10, same thing. Fill in the numbers, pH now is 8, pKa will be 10. Do the same kind of math. Move the 10 to the other side, it's -2 now. Take 10 to the x on both sides, and now it's a smaller number. So this is interesting because in the ileum, the pH is higher, and it's still going to be mostly protonated, and that's just because it's kind of a highly basic amine. So there's a little bit of a weird situation because we know of Prozac to be a pretty well orally bioavailable drug, but it still is more protonated than not. It's literally about 1% neutral, 99% ionized. So this could be a case where the drug is actually maybe absorbed through paracellular space, or maybe it's actually absorbed in this protonated form and it transitions to the membranes. So I'd say there's a little bit of an odd situation. It's a little less clear-cut than the other ones. So it's better, but it's still poorly absorbed. Maybe absorbed in an ionized state, or maybe absorbed through one of these other absorption methods. Okay, so onward. Let's move on to the concept of aqueous solubility, and of course a drug needs to be soluble, aqueous soluble, for it to dissolve in blood and reach a drug target. You know, to be in the liquid in our body, which is an aqueous environment. So there's kind of two measures of aqueous solubility: log P and C log P. There's many more, but these are the ones we're going to talk about. So what's log P? How's it determined? This is kind of a classical technique. It's a partition coefficient, and you can basically imagine if you had a separatory funnel with octanol and water in it, and you allowed the drug to be in this separatory funnel, and you can measure, and it happens to be that octanol and water are not miscible, otherwise this wouldn't work. But you can measure how much of it's in the octanol, how much is in the water, and then that would be, you take the logarithm of that and get a number. And so P is basically the concentration of the drug in octanol divided by the concentration of the drug in the water phase. Take log P, and it's basically the logarithm of that number. Okay. So for drugs, the range of log P basically goes from 0, which is extremely polar, to 7, which is extremely greasy. And then, you know, an optimal drug is somewhere in the middle, so not too greasy, not too polar. So why does it matter? Why does solubility and lipophilicity matter? If it's too polar, it's not going to transition through membranes, and if it's too greasy, it's usually going to be insoluble, so thus it needs to be somewhere in the middle. It needs to be dissolved in aqueous solution, thus somewhat polar, and in our body to be active and reach a drug target. The drug also needs to be sufficiently lipophilic, greasy, to pass through a bilipid membrane, often in the intestine or the stomach, and also through various cell membranes to reach a drug target. So it's a little bit of a trade-off between too greasy and too polar. And some drugs also need additional lipophilicity to cross the blood-brain barrier, which is even more of a greasy membrane. And C log P is simply the computationally determined version, which is really cool that we have computer programs that allow you to calculate this very easily given a chemical structure, and not need to do this experiment with a separatory funnel and using octanol and water. Okay, so all right, aqueous solubility, a little bit more about this. And C log P is incredibly convenient, and we can do it on the computer. We can also maybe have it 10,000 molecules and feed them through a computer to get those numbers without needing to do a lot of experimental work. There's a lot of different algorithms, countless algorithms for C log P determination. We're not going to go through very much of these, but we'll show at least one program, free web-based tool that does the C log P calculation. And we're going to use something called mole inspiration, and you guys will be doing this too in a little bit after I show you how to do it. Mole inspiration is a free website. It's not, not superb, and the interface isn't superb, but it does allow us to do these basic calculations for free. Now their algorithm, they take C log P, they call it MI log P for mole inspiration. So it's a slightly different variation, but it's a reasonable calculation based on they look at the chemical structure, and they each of the parts of the chemical structure can be added up to make this value. Okay, so epinephrine, also called adrenaline, they calculate MI log P as negative 0.06, and is that polar or nonpolar? You know, on this scale, 0-ish is is very polar, and it makes sense. You have, you know, all these hydrogen bond donating groups. The alcohol, the amine is likely protonated. So a lot of polar functional groups. So this is a very polar drug, and it's also, you know, it's a neurotransmitter that your body uses naturally. Aspartame is NutraSweet. This is also an extremely polar molecule. We don't really use it as a drug, but it's used as a artificial sweetener. And in, you know, in aqueous solution, the carboxylic acid's deprotonated, and the amine's protonated. So it's a thing called the zwitterion. It's like a biological. A lot of amino acids do that kind of thing, right? Hydrocodone, which is a opioid derivative, so it uses a painkiller, and it is a little more greasy. The number's a little larger, as expected, and we do have some polar functional groups, the ketone and the ethers and the amine and stuff, but it's a little more polar. It is an orally available painkiller, anesthetic. Hydroxychloroquine, which is uses a anti-malarial drug. It has you know, this quinoline derivative. There's chlorine, a couple other sort of polar functional groups. It's a little surprising this is such a maybe a higher number compared to the other one, but this is I think it's also the greasy chain and various things like that will enhance its log P. Prednisone, of course, is the steroidal anti-inflammatory drug. This is it's steroidal, which is generally going to be very greasy. However, it also has some polar functional groups, and the 2 alcohols and the 3 alcohols, I guess, ketones, etc., etc. So it's it's still pretty small numbers. It's a little surprising also. Estrone, the female steroid hormone, is getting a little larger. It is a steroid, but it also has a hydroxy group and the ketone. Cholesterol, as expected. I mean, this is a really greasy molecule. This isn't really taken as a drug, but it's a component of your cell membranes and things like that. But its log P is about 7.62, so almost like it's in the extreme end of the spectrum. All right. Okay, so done with the log P stuff. Another tool, or another parameter, I guess, is called polar surface area, which is pretty logical. You know, it means the surface area of polar functionalities. In some ways, it's kind of analogous to log P, or maybe inversely related, because the larger number of polar surface area is going to be more polar. Okay, and there's going to be a couple different variations of this, the PSA and the TPSA. Okay. So the polar surface area. It's another parameter, and it's used in some of the rules we'll be talking about, Lipinski and Weber. It also predicts membrane permeability, so that's a useful thing, and useful for predicting drug likeness. Like, does it act like a drug and have predicted bioavailability? Okay, so PSA and TPSA are estimates of the surface area of the molecule that has polar features, and that could be polarized functional groups, not necessarily ionic, but hydrogen bond donors, maybe hydrogen bond acceptors, etc. So typical numbers range from 0-ish to 200 or 300, which are highly polar substances. So this polarity is complementary to C log P, and I would say it's maybe inversely complementary because it's opposite. We also, this is convenient, we use this mole inspiration website to quickly and easily determine these values. Okay, so TPSA is a quick and easy and maybe more modern method of determining PSA, because it used to be a little more complicated. The algorithms have improved over the years, and maybe the classic approach in this case looks like a beta blocker type drug with the two oxygens and nitrogen. The classical approach, it's a three-dimensional approach, so it actually creates a three-dimensional model of the molecule and searches for the polar components of the surface, and eventually finds those atoms, and it estimates the number 53.2. Now, the alternate approach, in this PSA in this case, the alternate approach is to basically look up the little bits of the molecule and use a rule table, which basically eliminates the need to make a three-dimensional model. So it's a very quick and easy approach, and then make an estimation. In this case, it's 50.7, so it's pretty close to PSA in a fraction of the amount of time, computer time. So it's much faster, 2 to 3 orders of magnitude faster. Okay, so then there's these rules, the Lipinski rule of 5 and the Weber rules for drug likeness, and maybe a prediction of oral bioavailability. So these are what we'll see. It's a couple different groups. We're trying to figure out a way to quickly screen drugs for their drug likeness, and is it likely to actually work as a final drug? So there's the rule of 5 and the Weber rules, and they both kind of approach the problem slightly differently through different assumptions. So, in drug discovery, given a chemical structure, it would be ideal to determine the likelihood that it could be orally active drug. So the idea is, if say you're at a drug company and you're screening, 20,000 to a million molecules against a drug target, it would be nice to predict if any of these molecules would actually work as a drug, or if they have any liabilities or like parts of the structure that might make it not work too well, and do that very quickly in an automated fashion. So the Lipinski rule can do that, and also the Weber rules. So and it would be really ideal if you could do this using easy to find values like C log P, which is easily calculated, TPSA, right? These are numbers that we can quickly determine and not need an experiment. So there's a couple methods. 2 of the common criterias are, as you see above, Lipinski and Weber. So Lipinski rule of 5, we'll go through that one in a second, and then the Weber rules of drug likeness, which is almost like the rule of 2. It's like there's fewer parameters. You'll see those in a second too. A couple references for these if you want. There's a gazillion references on Lipinski rules beyond this and more recently. Weber is maybe a little less common, but it's another set of guidelines. The Wikipedia page on Lipinski rule of 5 is actually pretty good too. It's a kind of easy to digest, easy to read summary. Okay, so what's the rule of 5? Lipinski's rule of 5, RO5. So there's no more than 5 hydrogen bond donors. What is a hydrogen bond donor? These are typically OHs and NHs. So no more than 5 hydrogen bond donors. No more than 10 hydrogen bond acceptors. So this is usually going to be totals of N and O atoms. And so, so we can basically look for OHs and NHs and N's and O's to get this. Molecular mass will be less than 500 Daltons. So again, the rule of 5 kind of makes sense because we're seeing 5 a lot, or 10's a multiple of 5. Octanol water partition coefficient, which is log P or C log P or Mi log P, any of these things, is less than 5, because if it's more than 5, it's probably not very soluble. And the rule states that, so there's actually 4 rules that are all kind of around the number 5. And the rule states that 1 violation is allowed, but not like 2 violations or more. So 1 violation of the rules is okay. And the Weber rules of drug likeness may be simpler. There's only 2 rules. What are the 2 rules? One is there's 10 or fewer rotatable bonds. So that's not something that is considered in the Lipinski rules. So bonds in a ring are not rotatable. We'll show these rotatable bonds in a second, examples of it. But like single bonds that can rotate that are not in rings. Now, why does that matter? It might, if there's too many rotatable bonds, there may be it may be an indication that I think it's like maybe a difficulty getting into the membrane. There's too much entropy. I didn't really understand the reasoning for the rotatable bonds thing off the top of my head, but I think I learned about this before and I just can't remember. But that's one of the Weber rules. The other is PSA or TPSA is not greater than 140, and right it because as you get higher in PSA, it's going to be more polar, and if it's more polar, it's not going to go through a membrane. So at some point, they decided 140 is the cutoff. Both rules have a lot of exceptions, but they're still regarded as good guidelines in preclinical drug discovery. And I mean, to be safe, maybe you can use both rule sets, right? And we're going to practice these rules in a second. The Wikipedia page, if you want a little bit more context. I don't know if the Weber rules has one, but I know the Lipinski rule has one. Okay, so examples of these rules. All right, so here's the rules again. With Lipinski, one violation is allowed. So let's look at some examples. So this is what molecule is this? Doxorubicin, yeah. Okay, so doxorubicin, this is showing the Lipinski rules on the left, Weber rules on the right. And so hydrogen bond donors are 7, and you should be able to count them, I guess. 1, 2, 3, 4, 5, 6, 7. So this has 2. The NH, there's 2 hydrogen bond donors on this NH2 group. Molecular weight's 543. C log P is pretty small, so it's pretty aqueous, and or it's pretty polar. And hydrogen bond acceptors are 12, so that's all the oxygens and nitrogens. Let's see, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, okay. For the Weber rules, rotatable bonds is 11. That's sometimes a little hard to see, and I think the tools give you that number also. PSA is a little bit on the high end, and total H bonds is not something. I don't think that it is part of the rules. I don't remember seeing that. Okay, so anyway, there's 2 Lipinski violations right off the bat. I mean, the hydrogen bond donors are large, the molecular weight's kind of large. C log P is correct, and the H bond acceptors, it should be less than 10 or 12. So we'd probably argue that this is too many Lipinski violations. So in this case, rotatable bonds is 11. And that's all a little high. PSA is high. and then the H bond, and H bonds is not something that's being considered. But anyway, this actually kind of matches because it has an oral bioavailability of 5%. So it actually can be used orally, but it's a very poor bioavailability, as expected by these two rules. And the guidelines are pretty much all exceeded except for the C log P value. So as it shows, I mean, it is a it's an orally available drug with poor bioavailability. It's a cancer drug, if I remember. Okay. Rotatable bonds are hard to count exactly. I actually counted 12, and I mean, we look at each one of the single bonds, and it's kind of hard to do, and I'm not going to do it again. But when I did this earlier, I was able to count 12 rotatable bonds. This is something that if it was on a homework assignment, I would probably just give you, because it is a little hard to count exactly how many rotatable bonds there are. They actually have a definition in the Weber paper. Rotatable bonds are defined as any single bond, not in a ring, bound to a non-terminal heavy non-hydrogen atom. So it can't be a bond connected to a hydrogen. Excluded from the account were amide CN bonds, because amide CN bonds are kind of non-rotatable. They're like sort of like a double bond. There's a resonance argument for that. Okay. Another example. Okay, so this is a molecule neuropeptide YY1 antagonist, and we're showing the Lipinski parameters. There's also it's 2 micromolar potency, and I think that we'll come back to that. Okay, so anyway, looking at the Lipinski rules, hydrogen bond donors is that obey or not? It's less than 5, so it seems to be valid, or it follows Lipinski's rules. Hydrogen bond acceptors is 3. Hydrogen bond acceptors is 3, because there's 3 nitrogens and oxygens, and yeah, and that actually seems to be okay. Molecular weight less than 500, good. Log P is 5.7, so that actually would be in a violation. Polar surface area will be used for Weber, and it's 17, so it's a pretty small number. That's pretty on spot. Rotatable bonds is 6. So it looks like everything's pretty good here for the. I calculated the rotatable bonds a little differently. Potency is I think it's pretty bad for this drug, but those parameters are green. That is a little high, so that'd be a Lipinski violation, but you get 1 violation anyway. And then the polar surface area, so it pretty much matches Lipinski and Weber. The problem is not the drug likeness, but actually the potency is a little bad. So this isn't necessarily a good drug, but it's not because of the structural features. It just binds poorly to the target. And in this case, what they did is they converted it to a different molecule, but then it had problems too. So it's this drug discovery for you. So they took this molecule with good drug likeness but poor potency, and they converted it to this molecule. And then now they're actually at 1 nanomolar, so you can see that potency got boosted quite a bit. But it'll have some oral absorption issues, as we can see. Hydrogen bond donors, there's only 1 now. Hydrogen bond acceptors, if you count all the nitrogens and oxygens, it's 6. Molecular weight's a lot higher, so that's beyond Lipinski. Log P is too high now, 7.3 versus 5. PSA is fine. Rotatable bonds is too high now, and I calculated 12 when I did this earlier. But nevertheless, it looks like it's in violation of Lipinski. Good potency. poor oral absorption. Those two parameters are good. Those two parameters are bad. So Lipinski only allows one violation, so we have a problem here. And then these are that is actually good, and that's bad. So generally speaking, it violates Lipinski and Weber. So there's an opposite situation: potent in an assay, but not a good drug due to absorption. So this just shows the well, some of the struggles we have in drug discovery. All right. So I'm moving on to some of these computational tools, and I want to talk about something called SMILES first, which is a pretty standard format for representing chemical structures in small molecules. And then we'll talk some about some of the various tools to manipulate SMILES and to, that we can use to either create SMILES or figure out these molecular properties. Also use the determine the drug likeness. All these kind of fun things. All right. So SMILES is a chemical structure representation format. Forgot when it was developed. Yeah, 1980s. Wow, it's been a good while ago. Improved through the 2000s. So this stands for Simplified Molecular Input Line Entry System. And for different drugs, there's these SMILES strings, and it's pretty cool. I mean, thinking about this molecule, for example, ciprofloxacin, that you could represent the chemical structure in just a series of letters, which is kind of amazing. This kind of shows how it works, and of course you don't need to know this, but it just shows it's not magic. It breaks each of the the rings into strategically breaks the rings into these pieces, so it turns into this kind of linear string of molecules, and it represents and it shows the rings actually in the text. And so this kind of shows how there's basically just a series of fragments, and then the rings are just sort of connected. Kind of a cool approach. They figured this out in the 80s, which is pretty cool, because I guess, I mean, it was kind of earlier in the availability of even computers, like we certainly didn't have the computer capability in the 80s that we have now. Anyway, so this structure basically turns into this string of letters, and like when you see like the 1s and the 2s and the 3s and the 4s, well, you can kind of see that in the text, and that sort of shows like some of the connectivity, I guess, and N1 might be connected to carbon 1, etc. I don't know. I mean, like interpreting this text and being able to figure out the structure is not something that we as humans can do very easily. But what we need to do is be able to appreciate this cool idea, and that we can represent chemical structures as a string of letters, and we can download them, we can look them up, etc. So this is a pretty cool idea. All right. So there's a Wikipedia page on SMILES. It's pretty good and comprehensive if you want to learn more about just the concept of SMILES strings. There's also this website. I haven't checked if it's still active, but Daylight is a company that does a lot of chemical informatics stuff, and they've done a lot on SMILES development and like improving the protocol and the definition of the language. It's cool that we can look up SMILES for molecules. The PubChem database is a government website with a lot of molecules and pharmaceuticals, And we can also, another thing we can do is draw a molecule and come up with the smiles. Even a molecule that's unknown, has never been seen before. So it's pretty cool that we can either look molecules up or actually draw them. So some examples of this, I guess. All right, so methyl isocyanate is a very simple molecule, and just this shows the smiles. And again, there's not something you would do, but it allows you to appreciate how simple it is. Methyl isocyanate is CH3N double bond C double bond O, and the smiles is pretty logical. We're not showing all the hydrogens and stuff, but it's really CN, which is CN double bond C double bond O. So it shows the double bonds with equal signs. That's pretty simple. Vanillin, how did vanillin work? Let me see. Vanillin has a benzene in it, and it's a pretty simple molecule. It's got an aldehyde in it also. You can see that there's probably the aldehyde with the C double bond O. And then they use this sort of one terminology to connect a ring, and they show oxygens at the right places. But anyway, that's just kind of just showing it's not magic. They have it's a very systematic method that we can use to determine chemical structures and draw them, and convert them into these smile strings. Usually computer programs do this kind of stuff nowadays. Okay. There's also something called isomeric smiles, which encodes absolute chiral configuration, so things like RNS and the Conning-Gold-Prelog rules. And so this is great because if you have a chiral molecule or you have a lot of these stereogenic centers, that is encoded into the smiles as well, and very useful for optically active or chiral drug-like molecules if we're using smiles to represent their structures. So here's an example: nicotine, and pretty simple molecule. The chirality part, which is this one chiral center, is represented in the brackets. I don't exactly know how they do that, but that's the chiral center, the stereogenic center right there. And then otherwise, there's basically two rings, and there's the kind of the oh yeah. Another thing, the lowercase letters I think have to do with the aromatic rings, and the uppercase letters are non-aromatic. So there's something about maybe the hybridization, which is why it's lowercase and uppercase. Okay, so looking up smiles is something you'll do in your homework. So one of your little activities. You can do it now too. We're going to go to this website, PubChem, and it's a NIH-based website. And then we can look up smiles. Sometimes there will be isomeric smiles. Otherwise, there might be canonical. Canonical is like for achiral molecules. So if you have an option, you usually pick the isomeric because it has the absolute chirality in it. If you only have one, if it only has one smiles, that's the one you're going to look up. We'll try a couple of these. Desipramine, which is a tricyclic antidepressant. Let me see if I can do it real quick. One second. And if you're following along on your computer, which I hope you do, you can't obviously copy and paste out of my YouTube. I wish you could. But you can copy and paste out of the PDF file. So that's what I'm doing right now. I'm copying from the PDF. So so I copied the HTML, the PubChem thing. Now I'm in PubChem. And what am I looking up? Desipramine. So I can search for desipramine. There it is. Desipramine. So PubChem is also just a really good informational website, and it actually has the smiles right there, so you can just kind of copy and paste it. There's also there's a free base form. There's a hydrochloride salt form. We can also go inside dicypramine. It has a lot of information, the CAS number and some other alternate names. It has some information about its biological activity, etc. There's the structure. Anyway, the point is you can find smiles, and you'll be doing this in the homework also. So and copy it and paste it, or use it in another tool or something. Fluoxetine. I'm not going to do all of these, but fluoxetine, Prozac. Well, we'll keep going with this a little bit more, just to see how to do this. Fluoxetine has a chiral center, but I think it's usually racemic. So fluoxetine. There's the molecule. Yeah, it's chiral, but it usually doesn't have an absolute stereochemistry. So it's probably going to be a canonical, or yeah, there's the smiles of it. What's the next one? Darunavir. This is an HIB protease inhibitor with some chiral centers, so it's definitely going to have a little bit of that isomeric smiles stuff. Darunavir. Search. Okay, so this is a more complicated chemical structure. I'm going to go ahead and click it. Yeah, I click it. You can see there's multiple stereogenic centers. If I go down to the smiles part, 1 second. Yeah. This one, it looks like, if you see the little brackets, it's isomeric. So this actually has these little brackets indicate that the absolute chirality is saved into the file. So this looks like an isomeric smiles. Anyway, I'm able to copy it and paste it, as you'll be doing in your homework as one of your activities. We'll do one more. Daptomycin. Antibiotic. Look at this crazy molecule. So it's a cyclic peptide. That's probably not the way this actual structure looks. It's probably a little more folded and interesting, but it does have a lot of stereogenic centers, and the smiles is here. So I guess, yeah, they used to have, like, both forms, the canonical and the isomeric. I think they just only show the isomeric, which is great because that's what you care about. So this should have all the stereogenic centers. Okay, so anyway, we're done with that. Isomeric encodes absolute chirality. It's preferred. If you ever have the option, you should look for the isomeric smiles. How to draw molecules to determine smiles. Okay, I redid the slide a little bit better to not show the structure. So, continuing. Yeah, so to draw a molecule to determine the smiles, there's a couple really good tools. This one, this Cactus NCI.nih.gov, is a tool that's on the National Cancer Institute website, and it seems to work really well. So we're going to try this out. I'm going to give you a little tutorial on how to use it. All right. So I'm going to go to my PDF off the screen. I'm going to copy this. Yeah, well, let me just do it here. I'm going to copy this link, and then we're going to go to it and try it out. All right. So I'm going to my PDF. Opening up a browser. Actually, here it is, right here. Yeah, it's the Cactus NCI.nih.gov. Okay, so in order to do this, we need to press the start structure editor button, and you can do this again simultaneously on your computer. And it shows this thing, this little JSME molecular editor thing. I think it's a Novartis product, yeah. It's a program that Novartis created for this purpose. I'm going to minimize the other window, and now I can see the editor. Okay, so let's see. And I'll continue to the next slide, or I'm going to continue my PowerPoint here. Okay, so this is one of the molecules that we studied earlier as one of your homework assignments. Homework 2, compound 5, and is a non-nucleotide reverse transcriptase inhibitor of HIV. So let's see if we can draw it and figure out the smiles. And you can, again, you can follow along, and it might be the easiest if you just follow along with me to learn how to do this. So can I make this larger? Yeah, I can't really make it larger. But anyway, so it's a pretty simple program. If you've never done this before, it might take a little bit of time. I usually go left to right. I'm going to work on the left side of the molecule, maybe just kind of build it and fill it all in and see what happens. So I'm going to start with the benzene on the left. So I click the benzene button. There's the benzene. There's my left side benzene for this molecule. And then how big is the ring? The big ring, it looks like it's 7 maybe? 1, 2, 3, 4, 5, 6, 7. Yeah, 7. So, and they have ring sizes up top. So there's like a 6, 7, 8. I'm going to just press a 7 and click that and fuse it. So I just go to the right side, click it. Now I have the 7-member ring. And I'm going to start adding stuff. Maybe I can add, I have different philosophies on this. Maybe I'll build those rings and then eventually add all the oxygens and nitrogens. I don't know. There's a lot of ways you can do this. Maybe I'll try a 5-member ring. I'll do this little 5-member ring right here. Okay, there's the 5-member ring. I'll add the ketone later. In order to do this stuff up top, we have an ethyl and a benzene. What I've found to do this is use the line drawing, the little line button thing up here under the white box. And I'm going to go to this carbon and I'm going to, let's see what happens. I'm going to click once, twice. Can I click 3 times? Yeah, I can click 3 times and then I'm going to, I want to add 2 things, but I want them to be far apart from each other. So what I'm going to do, it looks funny, it's 5 bonds to carbon. You know, we call that Texas carbon because everything's bigger in Texas. And that's because it's an expanded octet. You can't do that, that's illegal. But I can do it now. I can erase one of them, and I can go to the little red X by the new button. So I can hit the red X, and maybe I'll delete the middle one. So, okay, that's, I don't know. It still looks a little funky, but it's fine. And now I'm going to add the ethyl, second carbon of the ethyl. So I'm going to click the line button, and I'm going to maybe click up. Yeah, that looks pretty good. It's different than the orientation is different. That's okay. And then the benzene. Let me see. Maybe I like it because we're gonna have problem with the benzene and the ketone getting in the way. So maybe I'm gonna change my mind and I'm gonna add this guy. Let's see. How should I fix this now? I'm gonna take a step back, guys. Sorry. It's not the best editor. I mean, obviously ChemDraw is a little bit better. I'm going to try to do this slightly different though. So let's go to the 7-member ring again. Okay, draw my 5-member ring on the bottom. Yeah, if you have access to ChemDraw creates smiles much easier, but that's a expensive program. Okay, so I want to work on this ethyl and the benzene thing. I'm going to do it slightly different. I'm going to do click, click, click. But now what I'm going to do is maybe delete with the red X the right side one. Maybe I want to make that ethyl, but I do want to poke it to the left. The way I'm going to do that is I'm going to click twice here and maybe again up top, and now I'm going to delete here. I think that's going to work a little better. There's my ethyl, there's my benzene. See, that's a little closer and nothing's bumping into each other because this is not a super smart program. It doesn't do AI or anything, you know. So this is most of the structure. Now I just have to fill in my oxygens and nitrogens. So there's an oxygen. To do the ketone, I either use the double bond tool or just make 2 single bonds. There we go. Click once, click twice. Now I got a ketone. Nitrogen right there. Then I have my double bond and my double bond. I just use a single bond tool and click there and click there. So I got it now. It took a couple times to get it, but it's a doable utility. What else about this? Oh yeah, if you want to delete atoms, or I don't know if it does it have an undo. Control Z. Oh, it does. Control Z. It does undo on my PC. I also think you kind of need to do this on with a mouse or on a computer as opposed to a tablet. I just don't think it works too well with a tablet. Maybe you'll have better luck. But I want to save the smiles. Let me see. There's a little smiley face. Let's click it. And oh, there it is. There's my smiles. So I can copy that, and maybe I'll put it in a little Word file. Maybe Taxol in there. But anyway, there. Did it work? Copy. There, I copied it into like a Word file or whatever. Maybe I'll use that Taxol later. Okay, yeah, so you can copy and paste it, and then maybe into a tool or whatever. So you can draw molecules this way. Okay, so I want to move forward to my PowerPoint. So this is a chiral molecule. It's got 3 stereogenic centers. And that's going to be a little more challenging to draw. So let's try it out. Okay. So back to the editor. How do I delete this thing I drew? I think the white box on up by the smiley face deletes. Yeah. Okay, and now this is the notch 2, notch 3 inhibitor that was in your homework problem set number 3. So let's try it out. I'm going to do the benzene on the left. How big's the ring? Another 7-member ring. Yeah, kind of similar to your HIV drug up there. 7-member ring. Okay, so how do we start putting this together? I'm gonna just kind of gradually try to do it, and I think one interesting thing that was a little difficult because I tried this just a minute ago. This nitrogen on the hanging off the right, to make it horizontal like that was a little strange. So the way I did it is I click once. Oh, I actually did it right. Oh yeah, maybe that's fine. Okay. I'm going to start drawing some of the stuff in. The nitrogen up here. The C double bond O up here. To add that methyl, I think I do the line and just click on the nitrogen. Double bond there, nitrogen. The benzene, the pH, I'm going to do a line. Click, benzene. Okay, now it's going to, I'm also going to do the chirality at the very end, so I'm not going to worry about chirality initially. There is a little issue here, and I just remembered what the issue is. Because this is going to be a nitrogen. I can draw a nitrogen, sure, why not? But I'm not going to do chirality till later. Okay, so if I want to make this look horizontal, which I think looks kind of nice here, I had a little bit of trouble. So what I did is I click once, it went the wrong way. Click again, went the wrong way. Click a third time, and now it went horizontal. And then I hit the red X, and I'm like, okay, now I delete this, delete that. Okay. Why is it NH2 though? Can I just click once? Click nitrogen. Maybe a better way to do this part. Okay. See, there's a little bit of troubleshooting. I'm going to click once. I'm going to keep it carbon for now. Now I'm going to click once. Okay. That now I can maybe I'll add the C double bond O. Like if I want it to go one way but it goes the other way, I click it and I delete it. So here we go. Now I think I'm ready to maybe delete these two methyls, put a nitrogen there. That's actually pretty cool. That worked. And now I'm getting there. Now that goes down. Okay, so let's see. Nitrogen. This will be a C double bond O. Click. Click. Make a double bond, make it an O. Alright, so there's my C double bond O. To continue this structure, and I just have to get the structure right, I want to go off to the right. So, oh no, it went to the left, so I click again, now it went to the right, now I delete it. See the little game I had to play there? Okay. I want, off this carbon, I want to show the 3 carbons, CH2, CH2, CF3. So now I'm going to go click once, click, and I want it to go down just because that's the way I like it. Down, and then it'll click again, and then eventually clean up, use the red X. See, it's a little funny. 3 carbons, 1, 2, 3, 1, 2, 3. For the fluorines, the CF3, I actually think you have to do 3 bonds. Click, 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 and those are going to be fluorines. Now I hit the fluorine button. F, F, F. Okay, we're cool. Alright, coming along, and now where do we go? I can't reproduce exactly how it looks, but I can still reproduce the structure. So now I'm going to go down. There's going to be the amide. Click, click, click. And now I can make the amide, double bond O, NH2. We're good? Now I want to do that other 3 carbon piece up top. Again, we'll do chirality at the very end. So I want to make it, as long as it goes upward, I don't really care the angle. So it'll be like up, over, up. Okay, now we have the 3 carbons. And we need another CF3, so I'm going to do the line, and I'm going to click, click, click. Okay, so now I can do my FFF. Beautiful. Okay. And now I want to do chirality. The chirality is really easy. There's only one chirality button, but you can like use it for other. You can use it once or twice to get the chirality you want. So I click the chirality button under the smiley face, and I want to do the left nitrogen. So I'm going to click in there right on the bond, and okay, they did it. It wedged it. So that's wedged, just like it needs to be wedged. And then this one needs to be wedged also, right? So I just click it. Ah, it wedged it. Very nice. And then this one's got to be dashed. So the way you do that is you click it once and then click it again, and now it's dashed. So that should be cool. And now all I'm going to do is I just want to get the smiles. So let's try it. Smiley face. There it is. It's isomeric because you see all the brackets and stuff. Yeah. Click the whole thing. Right click. Copy. I'll go to my Word document and paste that one. Okay, so that made it nice. Okay. I'll minimize it. Hold on to this thing. All right, so we did that one. That was a little more challenging, but not that bad. Okay, this is a COVID-19 protease inhibitor. We used this in one of the homework assignments previously when I taught this, and I don't know if we're going to get to it in this semester, but it's a nice molecule, and it's definitely a lot harder to draw, and I wouldn't try to draw it. But if you need this, we may need this for the homework assignment. I'll just give you the smiles. I think for the other 2 molecules, I'm going to have you do them, and then you'll have to calculate properties or use my other little tools and stuff. Alright, so continuing. So now we know at least how to create smiles for pretty simple molecules, including with chirality. Next thing. If we're given a smiles string, can we use it to identify a compound? And that's a great question. So like say I'm given a smiles string. You know, it's a way to represent a structure. You can't really see the structure by looking at the smiles, but would you identify it and see like what molecule is it? And the answer is yes, we can, and we can use the PubChem database if it's a known molecule. If it's an unknown molecule, of course, PubChem won't know how to identify it. Let's do an example. So here's a long smile string, and let's see if we can identify it. And so what I'm going to do is I'm going to go to the PDF file on my computer, and let's get the PDF file. Okay, I just copied the smiles, that smiles on my PDF. And so one cool thing is PubChem allows you to just search a smiles, and let's try that just for fun. Delete. Let's get back to PubChem. Delete. Okay, we're in PubChem. So as you can see, if we're looking at the bottom of this, we see smiles even. So you can search for a lot of things in PubChem. So I'm going to paste the smiles, and here we go. Oh, there it comes up. This is Tamiflu. It's a influenza virus inhibitor, or it's an influenza virus drug. I think it's a neuraminidase inhibitor or something. But anyway, so this came up and allows us to identify it, and there's all the background on this drug. So anyway, yeah, it's nice. One nice thing about PubChem is you can search for molecules. Great. What else do we got in the PowerPoint? So we did this. So yeah, antiviral neuraminidase inhibitors used to treat influenza. And neuraminidase is a very interesting enzyme, and it's related to the sugar metabolism in the virus. And it causes it to be infectious. So this is one of the drug targets for influenza. Generation of 2D and 3D structures. I'm probably going to start this and then continue next time, just because I'm trying to have you guys do some of this yourself, and it's a little bit of a slow process. And we don't need a super long lecture either at this point. But let's maybe a closing point. Generation of 2D and 3D structures. So given a smiles string, can we determine and display a 2D structure or a 3D structure, a three-dimensional structure of a molecule? And you can, and there's tools for that. So, smiles to 2D and 3D structures. So also we need a little tangent here. How to save a screenshot. You guys know this, and I just want to make sure that everybody is able to do this. So, like if we have a structure on the screen, how do you save it and paste it into a molecule or a file, like a Word document? Yeah. So on a PC we use Shift Print Screen. So there's a Shift and a Print Screen button, and I'm going to probably. I usually open the file into a graphics editor. I love this program called IrfanView. It's a little cat, I guess. I don't know what animal it is. And IrfanView is a free Photoshop for PCs. I don't think they have it for the Mac, but I'm sure you guys have Mac versions of things like IrfanView. And then we basically crop the image, make it smaller, and then paste it somewhere like in a Word document. Mac, I don't really have a good answer. I know the Mac people probably know this better. Somebody told me Shift Command 3 as a print screen type thing. As an example, let's do Taxol. This is we'll do it from the Wikipedia page. So if I open up, let's do that real quick. Wikipedia, Taxol. Okay, so here's the Taxol Wikipedia page with the structure. So one of the ways I could, if I wanted the structure and I wanted to put it into a document or something, I do Shift Print Screen, and then I print screened it, and then I'm gonna open up IrfanView. So IrfanView is a graphics editor, and then I just basically can copy out the structure. I can crop it, Control-Y to crop, and now I basically have that structure, and I can paste it into like a Word document. So there's my Word document, and now I've done that. So that's a way to basically take a structure from like Wikipedia or some other source, PubChem or whatever. What else? There's also there's a screenshot method which I just did. There's also, and that's basically what it looks like. There's also something called an SVG file, which is a format used on Wikipedia, which is I don't know how to explain it, but it's not a pixelated format. It's kind of like they call it vector format, which is very high resolution. I don't know. Well, without explaining the whole detail, one of the nice things is it doesn't save the background of the image, and you can actually change the background. So you can it allows you to change the background. And then here's an example, like where I saved the SVG file, and then I can set the background to anything I want. Just to show you how I do that, just because it's kind of a fun little computer trick. Let's do that. So if I go back to that Wikipedia page. Here's the Wikipedia page for Taxol. If I click the actual image and I click again, I think I can save it as a SVG file, taxol.svg. All right, save it. I actually have it already. And the way I'm going to do this, I'm going to have one second. A PowerPoint. I'm just using PowerPoint as an example. So here's a random PowerPoint slide, and I'm gonna just drag that SVG file into PowerPoint. Drag it in. Okay. So here's this infinite resolution image. So it's not pixelated. These aren't individual pixels. This is like a very high infinite resolution image, and I can actually set the background, because there's no background right now. It's just using the default background. So I can do right click, format background. I can say solid fill or gradient fill. I can pick some weird gradient scheme or whatever, and then it looks kind of cool. And so that's kind of the beauty of using these SVG files. And pretty much every chemical structure on Wikipedia is an SVG file, and you can download them, and that's kind of a cool creative thing. Okay, I'm actually going to stop right now. I think this has been a pretty reasonably length lecture, and I think there's not really a reason to just keep on going. And I'm planning to split this into next week as well. But I will show you what we will be doing next time, and we'll keep going. So if the next thing we're really doing is, for one, taking a SMILES string to create a two-dimensional chemical structure. Doesn't sound that exciting, but we're later going to need this when we start doing in silico synthesis and things like that, where we're creating SMILES from a synthetic reaction, and so we'll need this ability. And I'll just show you. There's a tool. It's on the UC Irvine chemical informatics website, and we'll go through that for ritonavir. And then also what we'll be doing is same thing, but for three-dimensional structure. So you can actually create a three-dimensional structure, which is pretty cool, and that's not a trivial thing. We'll do it for vancomycin and go from there. All right, I'm going to stop, and then we're going to come back next time. And next time will also be one of these kind of lectures. All right? Have a great night.